Sub-circuit. Sub-circuit is like when you have a circuit hierarchy. This is the module name A and module name A include B and C, etc. Sometimes we get the module A, B, C, D, D at the same hierarchy with the B, something like that. In such case, we define the sub-circuit. So for example, for this kind of a circuit, each inverter has the PMOS and NMOS inside. So this kind of instance is the sub-circuit. So we define that inverter with the sub-circuit definition, starting with the dot sub-circuit. The sub-circuit need to have an input and output. So input port information here, and this is the property we want to pass on to the sub-circuit. So we have inside the sub-circuit we have M1 and M2. So YA is the network we are seeing. Get the ports. We have the MMOS and PMOS, and all these kind of information are defined in sub-circuit with the dot ends. This is the example of the fan out of 4 inverter delay for simulation. So we use the sub-circuit definition. We are going to use that, and shaping we can change the size information, passing through some device size information that will change the loading, right? We'll see it later. This is the fan out of 4 inverter delay calculations by stack. So we want to construct starting from the pulse generator, PWL pulse generator, and then unit inverter here, X1, and then the fan out of H. So for example, so we H equal to, let's say, parameter H equal 4, so F times 4 and the additional times 4 and additional times 4 64, right? So additional times 4 56, something like that, right? So ideally, if the fan out is the same, right, all the delay per stage should be the same, right? As long as the CL. So the last inverter doesn't have any load, so up to this point, right? So starting from so this guy, we're supposed to have the same delay, but for the first inverter, it has some the waveform coming from the ideal pulse generator. So we define the pulse generator here, voltage generator here. So it starts from, according to this, it has a finite rise time and fall time, 100 picosecond rise and fall time, and the high duration is 500 picosecond, and this is the period. One nanosecond is a period. This is high duration. So it's a rise and fall time. So now we will take a look at the in this case, since the input rise time is assumed to be 100 picosecond here, but we are not sure whether that has the really true or not. So at the initial edge, you will have a 100 picosecond rise time, but as we propagate through the through the inverter chain, for the fan out of 4 cases, there will be finite slope will be settled. It may be 150 picosecond or 200 picosecond, whatever. So we have to wait until the edge is stabilized. So we need some kind of a stabilizing inverter stages until this edge is finalized. So that's why we add lots of inverter chain here to find out the fan out of 4. So most of the students make mistake when you simulate the fan out of 4 delay case. You just apply like a, let's say, infinite zero rise and full time signal. In that case, the inverter delay will be assumed to be much faster than the real case. Real case should be measured based on the real rise and fall time cases. So to make this, to find the, to measure the realistic delay based on the realistic rise and fall time, we have to cascade multiple inverters like this. Now let's see, now we have inverter instance here. So inverter is defined in the previous case, so we call the inverter. So between A and B node we add the inverter. Additional inverter here, the same inverter unit, but we want to increase the size by 4 times. In that case, we add m equal 4. So here h is parameterized, so we can use like a m equal quart h and quart. So this multiply the inverter 4 times, right? So we can similarly we can define this inverter instantiation. X3 again, A, B, C, and C, D, and inverter additional M equal to H times H, right? Something like that, right? So we can keep multiplying the inverter chain by sizing up by the H, right? So we will see in the following the spice deck in the next slide. One thing that I have not, one thing to note is that there's another option command like scale equal to 90 nanometer. So in the previous inverter definition sub-circuit, inside the sub-circuit, L was like 2, defined like a 2, and W is like, for example, some number like a 10. So 2 is quite large number, so we have to apply some practical case. So we add some scale factor 90 nanometer. That means when you define length of the transistor equal to 2, that means 2 times 90 nanometer. So 180 nanometer channel length, and W is also what in that case 900, 10 times 90 nanometer, so 900 nanometer width will be there. So there's some the scale factor there. And also supply parameter is defined like 1.8 volt, so this parameter is called here. So use of a parameter is like using the quart notation like shown in here, right? So the sub-circuit definition is called by the inverter like this. Inverter spice tag is included, right? Okay. The global command VDD and ground is that once this net is defined like a dot global, then the older the signal names signal node has the same name through the hierarchy will be connected, right? So let's say for example sub-circuit A and B and C, right? Or so you will have a inside it will have a VDD and ground node here, another sub-circuit, and let's say the H here, there are VDD and ground node here. If this name is the same, then all these are connected, right? If you define like a globally like this, right? But if you don't define like a global connect global keyword option like keyword like this, then the B and C the same, even though B has the VDD and C has the C sub-circuit has the VDD, those two nets are not connected. But if you define like a global variable, then the net is the connected. You just assume that those same node net is connected. So this option can be easily used for the VDD and ground, because the VDD ground is common for all the circuit most of the case. So we can define like that global keyword like this. Okay. Continuing here, 3, 4, 5 different inverter defined with the larger multiplication factor there. We have a transient definition here. We have a measure here. So actually our delay measurement is done on the X3 block. So for example, you have a X1 and X2 and X3. This is just something that we want to actually measure. X4, X5 for example. So when you make the step input there, the step input rise time is too fast, you will take time, several buffer stage, to settle some finite rise time. So if you look at each node's output, this is the actual delay output. So we have A, B, C, D, E, F. A is the input, right? A. And B is here. B, C, D, E, F, right? So we have in this example we applied like a little realistic rise time, right? That is similar to the internal output. Here is a little faster, a little slow down and slow down, right? Finally it slows down, right? Compared to here and there, it slows down practical with the number. So we measure this passing half VDD, 2 points, right pole. This delay is measured the optimization. So lec7Spice has the capability to adjust parameter automatically. So that's six. lec7Spice offers some optimization capability. For example, if you in the inverter, we can size, the MOS size is W1 and N1, 1, for example, W, and then PMOS is, let's say, P1. If you want to find the right size for the P1 to get the best performance, we can make this size of P1 parameterized like this, P equal P1. So and M equal as a 4, so the fan out of 4 delay cases. So we want to find the P1, so PMOS size to deliver the minimum delay or something like that, right? So in that case, we have to find the proper ratio inverter and the MMOS versus the PMOS size, right? So this we construct like this. So we add some parameterized definition there and run some optimization in the next slide. Here, parameter P1 is defined with optimization range between search for 4 to 6. The initial guess is 8. Right, you will try to find the model optimum, the maximum 30 iteration here. So you compute best ratio parameter. To search the best the ratio, so P1 over 4 is defined. So probably NMOS size is 4. So we want to find the PMOS size. So this is 4, and what is the P1? This kind of situation is probably assumed. So we want to find the P1 to maximize the performance. So what we want to monitor is that finally we want what average propagation delay. So average propagation delay is that, so we have to measure the output fall propagation delay, and then output what so fall to rise here, input is VC is the input and VD is the output, right? So fall to rise propagation delay. So input is going down and output is going up. So that we measure the triggering time, half VDD point here, we supply over 2. So we measure the delay between those two cases for the inverter delay. So this is a rise propagation delay, output rise propagation delay, and then output fall propagation delay is also measured. So we take the average of the propagation delay for rise and fall, and then also difference also measured. We want to balance the rise time and output rise propagation delay and output fall propagation delay. So final goal is to make it equal, I mean optimize to 0. And for the average propagation delay, we want to make the minimize. So our goal is to make it 0. So based on this keyword, we want to optimize, satisfy the goal, and then run the optimization process like that. So we have to set our target and goal and then run the optimization. Okay. So from the previous example, we can find that the PN ratio for equal rise and fall delay is 3.6 to 1. So PMOS is like a 3.6 times larger than the 3.6 times larger. This is for the minimum delay to achieve, right? This results in very big PMOS size. This typically very waste of the power too. So in actual, sometimes if you need the equal delay, then you can design like this. But in actual, the standard cell design provided by the foundry, they use the lowest average delay. I mean the rise delay, and so average delay, the average delay is the rise and the fall of the average. So they don't know what event will happen, whether that will be rise output or that whether the output will be fall. So what the in statistically what it matters is the average delay is minimized. So if you find the average delay is minimizing the ratio, PN ratio that minimize the average delay is 1.4. So for example, even though the rise time is slower than the fall time, this give us the average 73 picosecond delay. So this is actually most popularly used in actual typical the standard cell design ratio. But when you do the most of the custom design, you may choose differently. So depending on the actual design specification, you can choose whether you will get the larger or equal, whether you will choose equal delay or whether you want to list the average delay design. This is better for the low power. If you care for the actual performance, you may go for the larger PN ratio at the expense of more power. Power can be also measured in lec7Spice or the Spectre, any tool, circuit simulator. You can look at the actual power consumption. So average power is draining from the supply. So power PT, instantaneous power, defined by what? VT times IT. So time varying voltage and current, right? Out of what the supply, right? So these VT, from the supply the voltage is the same, but the IT will be time varying. So average power over some interval is something that you want to find. So if the circuit is periodic, like the switching, then if you just measure one period, then the average power will be same, right? If you measure like a 2 cycle or 3 cycle time, then you can get the same average value. But if you measure like a non-integer multiple of the period, like if you just average like this point, then you will get the wrong average power, right? So any periodic behavior must be counted, so you have to consider it. So if you don't consider like this kind of ambiguity, you have to average very long cycle, like more than 1,000 one, something like that, or 100, then you will get the, even though if you, like for example, if you average like 100 cycle, if you miss the wrong time point, averaging duration by 1 cycle, you will get the 1% error of your measurements, right? So something that so 1 cycle out of a 100, right, cycle, you may not properly get the power drain, right? So in that case, you will get 1% error. So as long as you know you are okay with such measurement error tolerance, then it will be fine. So you have to know that when you measure this kind of periodic behavior circuit and each power consumption, you have to measure some multiple time of a periodic period, right? So the average time is measured from 0 to 10 nanosecond. It would be better to this measurement time better to be multiple of a circuit period, right? So multiple of t period, right? Any periodic circuit, for example, clock period, right? In that way, you can get the better accurate power measurement. So this is the measurement keyword. So average is power. So power is measured, and average number is measured out of VDD. So VDD instance. This is instance name. So power is measured. Okay. So power in single gate. So if you wanna measure the power from the single gate, for example, VDD is, if you, let's say if you have a supply here, you have another block gate is also supplied from this DC supply source, and you have to isolate the current measurement. So current going into this gate, right, is measured. So you have to separate the VDD supply. You have to separate it, additional voltage source there, disconnect there, and then measure the power out of this single gate. But also you have to care about if the gate it has some finite input capacitance, the this other driving cell need to drive this input capacitance, and that means that the power to drive this gate is also drained from the other supply network supply voltage source. So uh, that should be like something that should be also counted when you calculate the overall power consumption. If when you want to minimize power consumption, if you just look at the monitor this supply gate of the supply, then you don't care about the input power. The input power is also critical, considerable amount of power consumptions there, so you have to take that into account when you optimize the overall power consumption. Okay, so you should not increase too much for this typical gate. So when you size the devices, we just size that based on the fan out, right? If you keep the certain fan out, then the delay over the stage will be similar, right? So that in that case, the overall performance will be the optimized. Okay. So this is one setup that we can measure the logical effort. So the third one is actually the device under test. As I mentioned, that we put some additional input gate to shape the input properly. So input rise time is properly settled there. And each stage we have a fan out of H. So typically, ideally, for the fan out of H, we get the same delay. And also we have a load setup, fan out load H, right? And also we put additional load, because when the load doesn't, if the load doesn't have the output, then it will have the faster output edge that will affect the input edge, right? The input edge rise and fall time. So the input edge will be affected by the output sharp edge, because if there is a parasitic capacitance always there. So this prevents us from measuring the proper delay on the device on the test block. So as you can see, whenever you build some test measurement, you have to always, this is always very important, always to model the input properly and output load condition properly. So without having input and output shaping the block, you will get the wrong data, a wrong simulation result. This is very similar to analog circuit design. For example, when you have an amplifier design, even in analog, most of students assume that ideal voltage source going into amplifier, and then there's no load specified at the output. This actually cannot properly simulate the amplifier characteristic. You must use the practical input resistance, because the the previous driving amp will have a finite output resistance, so you have to put some resistance there and signal coming in. Also, you have to put some capacitance there, because the driving inverter will have a input parasitic capacitance there. You have to, or load capacitance. You have to properly model input and output network. So both analog and digital circuit design methodology, you have to be very careful about modeling input and an output load, right? Otherwise, you will not get accurate simulation result. This is the logical effort. So we plot the simulation result, the delay versus the fan out of H to this point. If you increase the fan out, you get the increase the delay. So this is straight line there. We can see that this point is parasitic. This y-intercept point is parasitic delay, right? P. The slope of this guy is the logical effort G. So delay can be dAbs, is represented by G times P H plus P, right? The linear approximation. So this is the ABS, here the absolute delay in picosecond, right? Okay. So this is the simulated NAND gate logical effort for the input, 2-input NAND gate and 3-input and 4-input NAND gate. We have a different input and different rise and fall logical effort. Those are different because the circuit itself is not symmetric. So for example, for a 2-input NAND gate, we have A, B, and A and B. So A is on the top for the pull down network, A is on the top and B is on the bottom. So for example, for rise time logical effort, we have A has a larger than B, meaning the A input is slower for the rise time, because when the A input changes, we want to, let's say A from high to low, change as 1 to 0 transition, we want to pull up the output, but the A is close to the output, so there's a coupling capacitance there, parasitic, that will actually, so the output want to move up, but the input falling edge coupled to the output, it make it actually slower. So for the rising logical effort, A input is larger and slower. But for the falling logical effort calculation, the A is faster because for the A will just need to pull down the output capacitance, but for the B, you need to pull down this internal parasitic capacitance as well, because according to the Elmore delay, right? So you see more capacitance there for the B input. So, but eventually, when you take the average parasitic delay there, or the input A is slower, right? So input B is faster. You can say that, right? So the parasitic delay is greater for the outer, the input, right? And also we can find the average logical effort for the rising and falling, right? By taking average of those, right? So it's like this, right? So actual average logical effort is better than estimate what we just calculate by hand, right? Then the number we calculate by hand is a little larger than the actual simulation result. This is the comparison for the all different process we test here, different feature size F. It had all different supply voltage here. The fan out of delay is scaled down for better process, right? So approximately 180 nanometer process is compared to 350 nanometer, we get the almost 2x larger, smaller speed. About it at 2.5x slower, faster, something like that. So the feature size actually scales the delay similarly, right? But for 250 to 180, the tau is like 2x faster here. But what you see is the supply doesn't scale as much. It just stay 1.8 high, so we cannot directly compare the speed versus feature size. All the factors, supply and other thing also matter, so that roughly it just meet. So for example, 600 to 250, around 2x faster, right? here. Let's say for the logical effort for inverter, we specify that inverter logical effort is 1, and different logic gate, we say that the NAND 2 is the second best always, right? Second best, close to the inverter, right? Then logical effort. The NAND 2 is is fast. For the parasitic delay as well, we see that NAND 2 is also fast compared to other logical, logic block. So inverter, we have a parasitic delay a little larger than logical effort, so a little larger than 1. See, this is something that we can see the trend here, right? Definitely NOR is compared to NAND is a lot worse than NAND 2. So when you design a logic block, you just use inverter and NAND 2. That's kind of a way to design the faster building block. So any building block, for example, let's say, or whatever like this logic is required, then you can always convert that with the NAND gate and inverter by using bubble pushing technique, right? You can change the shape, the OR gate to AND gate by inverting input and output like that. Also here, change the polarity of the input and output. That becomes the equivalent circuit, right? Bubble pushing. So you make the equivalent in logic gate, and then from there you add the inverter like this. So here this inverter goes away, disappear, and like this, an inverter here, something like that. You can have now we have a NAND gate here, NAND gate, inverter there, and then you put the inverter there like that. You can always transform the logic with the NAND gate and inverter, right? So it is useful to construct any logic you want, right? Even the inverter can be constructed with the NAND gate. The NAND gate, if you are lazy and you don't want to design anything, then you just put inverter to input inverter and tie the input together. That will equivalent to inverter, right? Stuff like that.